So without further ado, I'd like to move into the program. It's my very, very great pleasure to introduce our first keynote speaker, Dr. Carolyn Porco. Probably most of you know her, but those that don't, she's had a spectacularly successful career, particularly recently. She is the leader of the imaging team for the Cassini mission, which has probably given us some of the most interesting insights on the potential of life in the universe. She's had a lot of other distinguished positions and working in imaging and on other missions like the New Horizons mission to Pluto and the Kuiper Belt. She received the Carl Sagan Medal from the American Astronomical Society. In 2012, she was named one of the 25 most influential people in space, and she's a visiting scholar at UC Berkeley. Carolyn? That's
So I want to thank the hosts for inviting me to give this prestigious keynote and be the opening talk at this conference. This is the first time I'm going to try to use my notes on something like this, and it's already not working. So I'm going to stick to the old-fashioned way. Cassini, as you couldn't possibly have missed, has just finished 13 spectacular years at Saturn. And in that time, we have we've had the opportunity to study in depth many phenomena and targets in the Saturn system, and therefore come to understand them very well. We have, I would describe it as a very sophisticated knowledge of many, many things that characterize the Saturn system. I'm going to devote this opportunity to tell you what it is we have found that caps the southern hemisphere of the small moon Enceladus, and why some of us now regard Enceladus as the most promising place in the solar system to search for evidence of life. And then I'm going to end with some of my own ideas about this thing searching for life that we want to engage in. So Enceladus is a very small moon. Okay, here it is alongside Saturn with the rings seen edge on in one of our beautiful early images. It is only a tenth the size of Titan, which is Saturn's largest moon. And Titan is about 50% of our own moon, and it is no bigger than England. And those of you from the UK should not be frightened by this, okay? It's not meant to be a threat. This is a Voyager picture, the best Voyager picture taken with a resolution of 1 kilometer per pixel. And it was pictures like this that told us that something radical had happened to Enceladus, that it had undergone internal activity, geologic internal activity, that on a moon this size was just very, very puzzling. And so, and we thought some of these areas, I don't have a pointer. Let's see if this works. No, it doesn't work. Okay, well, just the areas that look smooth, we thought they were smooth, and so we thought it had been resurfaced. And the only way this could have happened was because we knew also that Enceladus was in a resonance with the larger moon Dione. And that Dione imposes an eccentricity on the orbit, means the distance from Saturn changes over the course of an orbit. That means the tides raised by Saturn in Enceladus change also, and that flexes the moon, and therein you get tidal dissipation. But even knowing this at the time, this is the early 1980s, no one could come up with a way to actually melt the interior of Enceladus without using an implausible amount of ammonia, which would depress the melting point. So that's where it stood. We knew Enceladus was exciting. We didn't exactly know how it got that way. And also we knew, because it was discovered long before Voyager, sometime in the 1960s, that Enceladus was embedded in this donut-shaped diffuse ring of smoke-sized particles called the E-ring. So we knew that something was going on Enceladus, and two ideas came forward post-Voyager. One was there was charged particles impacting the surface of Enceladus, releasing tiny particles. That tended to be the preferred idea But there was, in truth, there was a paper that came out in 1984, just 3 years after the last Voyager encounter with Saturn, that said it could be geysers. There could be eruptions of water ice coming off the surface of Enceladus, producing the E-ring. So we had on the brain, especially we imaging folks, we had it in our minds that we were going to go in search of any eruptions that might be there on the surface. And I say this because in the press, when we finally discovered what we discovered, you know how the press are, scientists are completely taken by surprise. They're shocked. They never expected this. Well, that wasn't true. We did expect it. In fact, well, I'll say that in a minute. So Cassini. Cassini was outfitted like a Christmas tree. It had imagers and spectral analyzers going from the UV all the way to the long wavelength infrared. It had a magnetometer and instruments that could measure charged particles and characteristics of the magnetosphere. I have notes here to remind me. It had in situ instruments that were designed to scoop up the atmosphere of Titan, that would scoop up material and measure vapor in the case of an ion and neutral mass spectrometer, and then a dust analyzer. So an instrument that would measure dust particles. And it had stellar and solar occultation capabilities, and of course it had a radio science investigation that through Doppler tracking of the spacecraft, you could figure out the mass of a body if you flew by closely, and if you flew by closely several times, you could actually figure out the mass distribution. So once we found what we found, all of these instruments were brought to bear on the study of Enceladus, even the ones that weren't designed to do so. Another reason why we were so successful at Saturn was because of this tour. The JPL mission designers knocked the ball out of the park. This was a 13-year tour. It allowed us viewing from every possible conceivable angle. Over that time, we visited moons. We did a total of 127 close flybys of Titan, about 25 of the other satellites, excluding Enceladus, and 23 targeted flybys of Enceladus. And that doesn't even include the non-targeted flybys. The non-targeted flybys, we did many of those, and those were Voyager class. These were exquisitely close, and so that's part of the reason why we understand these bodies very well. Our first images of the plume were these, taken in January and February of 2005. We were in orbit for about 6 months. The top one, in fact, came down at about the time the Huygens probe landed on Titan. We were very busy for a very long period of time. And these images were designed to look for plumes. We deliberately used the opportunity when the spacecraft was at high phase, looking in the direction of the sun. It's a geometry that highlights tiny particles because of the process of diffraction. And so we discovered a plume. And in our images, whenever you see the plume, you're looking at tiny ice particles. But the magnetometer on Cassini, at the same time, during the same events, discovered the vapor component of the plume. And from this point on, from 2005, it was, do whatever we can to increase our coverage of Enceladus. So we began altering flybys during the prime mission and making changes to observations to get close to looking at this. And also, once the prime mission was over in mid-2008, Enceladus became a prime target for our mission extensions that went all the way out to 2017. So the plume arises from this area at the South Pole called, we name it the South Polar Terrain. It's a unique geological region. It's characterized by these fractures. This is a very false color picture. Enceladus is pure white, the whitest object we have in the solar system. And these fractures are, you can see them right here. Here's another look that was taken at the solstice, obviously. And this region is bounded by these continuous mountains and valleys and folds and so on. This boundary is something like 60 degrees south latitude, so that would be about the latitude of Tierra del Fuego. And we found a lot about this, this region. We found that there were, when we looked closer, there were these discrete jets erupting from the South Polar terrain. And when you process this image properly, you can see that they are part of a bigger plume that extends, in fact, into the E-ring. Well, on the imaging team, and in fact, in my research group, we planned a survey of the South Polar terrain to understand where these jets were. Did they have any correlation with other phenomena in the Saturn system? And for that reason, we got lots of very high resolution images, like down to tens of meters per pixel. South Basin survey. I forgot to say that this region is depressed. It's depressed about a half a kilometer. So right away, people figured out that's probably because there's liquid water under the surface. Okay, so here are just some images. We took lots of them. I just want to give you a flavor for what they look like. The upper one is our highest resolution. It's a mosaic of 2 images. And actually, if you look closely at this image, there's even material coming in between the jets. And so we could take all these images and triangulate the positions of all the jets that we could see, just like a terrestrial geologist would survey and figure out the location of a tree or a mountain. We did this with these jets. Oh, here's just another beautiful picture we took. And this is what we produced. We found this map. These are 2 sigma error circles of where the jets are. They're all associated with these fractures. And we had enough information that we could produce a 3D configuration of them. The heights here mean nothing. This just shows you the place and the orientation of the jets. Some of them are canted very much, but they're basically like fissure volcanism, if you know what fissure volcanism is in Iceland, for example. And another thing that was found by the long wavelength infrared instrument on Cassini was that there was a prodigious amount of energy coming out of these fractures. 5 gigawatts coming out of the South Pole. It would be like more heat coming out of Antarctica than receives at the equator on the Earth. When we look at where the regions of greatest jetting activity are and compare it to the thermal radiation, even at this low resolution, there was obviously a correlation. But then in my research group, we wrote a paper about this. You could see that there was a correlation. To within the uncertainties, there was a correlation, a coincidence between the jets and small-scale hotspots that one of the infrared spectrometers had found. Small scale, meaning they were no bigger than about tens of meters. And here they were, for this small region where they observed, they're coincident with the jets that we found. So this was a very important result because it told us that the heat, up until this time we didn't know was the heat producing the geysers or the geysers producing the heat, but it turns out that the small scale here tells us that this is heat that is latent heat of condensation deposited in the near surface of the conduits leading to the surface. By this time, we knew that the model was that there were fractures that went all the way down to a subsurface ocean. So anyway, this was that's what is producing the heat, at least that's coming out of the fractures. Now the other Cassini results, I'll just go quickly through these. Water vapor in the plume found by an ultraviolet instrument and the INMS. Ice particles. We deduced very early on, you see it's a 2006 paper, were coming from liquid droplets. We found that because the ratio of the mass in the solid particles to the ratio of the mass in the vapor was more than could be produced. That quantity was greater than you could get if the solid particles came from vapor hitting the vacuum of space, expanding, and then condensing. And that has stayed throughout the mission. That ratio is still greater than what you would get from condensed vapor. So we knew right from the beginning that this was sourced in liquid water. We didn't know the depth of the source. And we could examine the fall off in brightness, fall off in mass, with altitude, and we could find the mass ejection rate and how fast the particles were going. And it seemed then, and we still believe it now, there's only 9% of the material in solids leaves Enceladus. The rest of it snows back down onto the surface. I think that's very important when we're thinking about missions we want to send back to Enceladus. Most of the particles near the surface are rich in salts, salinity comparable to the Earth's oceans, and so that also says the salt-rich particles had to originate as droplets from a salty liquid reservoir. You can't get salt and ice any other way. And the liquid reservoir is in contact with the core. That was very important because it told us the source, the ocean, it was an ocean and had to be deep. And then the vertical stratification in particle sizes, the larger are near the surface, smaller at altitude. And all of this says the particles falling down to the surface are the bigger ones that come from the salty liquid water or reservoir. Or in other words, these are the ones that are the most interesting. They also, okay, so this is our model. This is circa 2014. It's mostly right. The idea is you have water coming up through these fractures. They go all the way down to an ocean. And the water tables could be as much as a few kilometers below the surface, but froth, water and liquid droplets and so on make it all the way up to the surface. You get condensation at the surface that produces the heat, and salt content and organic content greatest near the bottom, and the particles that escape are salt-free. Okay, I'm going to have to keep rushing. Something tells me I'm running out of time. So both vapor and ice contain organic materials. Mostly it's water vapor, but CO2, ammonia, and methane, they're all there to the tune of 0.5% or 1%. There were lighter hydrocarbons that were announced early on, but it turned out over the course of the mission that team, the INMS team, found that the lighter hydrocarbons were really being produced by collisions in the target, between the target and the material, with heavier hydrocarbons, heavier organics. So it was an indirect way that we inferred that there are actually heavy organic materials in the plume. And then sensational fine silicon-rich ice nanoparticles, which have been interpreted as silica particles produced in alkaline hydrothermal fluids at the seafloor. And then very near the end of the mission, H2, molecular hydrogen, which was taken as an indication of serpentization in association with hydrothermal activity. I mean, it doesn't get any more exciting than this. And then the body of Enceladus. This is, I don't know how I'm doing for time. Doppler tracking of the spacecraft told us what the configuration under the ice shell was in the South Polar region, and how thick the ice shell was, how deep the ocean was, and so on. And that a global ocean was possible, but it was indefinite. And then our measurements, our images of Enceladus at very high resolution over the course of the mission were used in an extensive analysis to pull out the fact that the body of Enceladus was librating. And it was librating with a tiny little amplitude of 0.12 degrees, but it turned out to be a significant measurement. And it's caused by the torque of Saturn on the moon's permanent bulge. And it's bigger than what a solid body would exhibit. And so we can infer from that it was there was an ice shell overlaying a global ocean. So this is where we finally figured out in 2016, Enceladus does have a global ocean. And this is sort of what we think it looks like. This diagram was put in a paper I wrote in 2014. It's out of date, and I'll tell you where it's out of date. We do think there's a hydrated porous silicate core. We think the ocean under the South Pole can actually be very much thicker. It could be as thick as 50 kilometers. The water layer, ice and liquid, is about 60 kilometers. The ocean could be anywhere from 50 kilometers thick to maybe 30 kilometers thick. And so at the South Pole, you could have a thin ice shell, or maybe an ice shell that's about 10 or 20 kilometers. So there's a lens, there's a regional sea underneath the South Polar terrain, as we long suspected, but there's also an ocean that goes all the way around, and it's much thinner elsewhere. And with a porous hydrated core, this is very important. As much as 20 gigawatts of tidal dissipation could occur under the ocean now. So in my diagram here, we thought it was the ice shell that was being tidally flexed, and that's where the heat was being deposited. It turns out that we think now the tidal dissipation is actually in the core. That's consistent with our idea that we're seeing evidence of hydrothermal activity, and that ocean water is actually being circulated through the core, and the fluids that come out are superheated. Okay, and then temporal variability. This is work that I've been doing with my group, and this has turned out, we have brand new results just as a result of this weekend. So here we have our picture again of the resonance between Diurnal and Enceladus. I just want to take you through this a bit because it's interesting, it's fun, it's also a little nerdy. Enceladus is synchronously rotating and in an eccentric orbit because of a forced resonance with Diurnal. Both the size and the orientation of the tidal bulge will change over the course of each orbit, and this is the way it looks. Here I'm grossly distorting the body of Enceladus. This is to indicate the variable tidal bulge, because there's also a permanent one that's not shown here. The arrow, think of the arrow as somebody standing on the prime meridian, and this is when Enceladus is closest to Saturn. This is shown from the reference frame of Saturn. And this is when Saturn is directly above. And then as Saturn moves, now it's further away, the body is not so distorted, and then it continues to move. And you can see this tidal bulge just sweeps underneath you as Enceladus moves on its eccentric orbit, and Saturn, therefore, doesn't maintain a fixed position but goes back and forth. Okay, so that's the simplest version of what's happening. And this is what happens on the surface in these fractures when that happens. So we have our diagram over at the left, and a sixth of an orbit later, the fractures go from being in compression and they start to open. A third of an orbit, after periaps, they are almost fully open. Most of them are fully open. And then at exact apoaps, some of them are still open, but not as much. So that's how the tidal stresses are varying on the surface. And Saturn's position in the sky also has long period variations. There is a libration of the 2-to-1 Lindblad resonance, 2-to-1 orbital resonance. It has a period of 11 years. And then there's also a co-rotation resonance. Think of the Neptune ring arcs. They're anchored by a co-rotation resonance that has a period of 4 years. And both of them should produce motions on the surface that are larger than the diurnal variation. In fact, this is the displacement of the prime meridian, that was that arrow in that picture, with the position of the tidal bulge, or Saturn in the sky above. The black is the diurnal variation, but the larger amplitudes are the result of the 4-year and the 11-year period. So we went searching for this. We knew early on that there was a diurnal variation in the brightness of the plume, or in the mass of the plume, and we figured out it was because the fractures are opening and closing and letting water come from below. But we went in search of these also, because we had the data to do it. And and we extended it out to 2045 because we know we're thinking about a mission to go back to Enceladus. So this is how we did it. We take a slab in the sky above Enceladus across the plume. We measure we add up all the brightness in there. And brand new results from my research group. This is the diurnal variation over the course of 13 years. And we go from 2006 to 2017, and the red ones are the most recent, just like the last few months of the mission. We saw the plume really, really brighten. This has given us a long time baseline now. It's not well sampled because we couldn't be observing the entire time, but we've got enough that we were able to do a periodicity analysis And you could see that there are two minima. There's two different ways to treat the data. Don't worry about that. There's two minima. And when you actually take the motions of the orbit of, the motions of Enceladus in the JPL kernels that they produce, just telling you over however long you want to know where Enceladus is, and you analyze those in the same way, you find these two distinct periods. There's a 4-year period and an 11-year period. And we could find them in our data, our plume data. And even better than that, when we take our data and plot it against time, and we actually just group the data in 2-year intervals, so those are the red circles, we get this, and it looks at first, well, that doesn't look like a very good match at all, but when we just phase shift it a bit, we get a pretty good match. So this is really recent. We haven't even published it yet, and I can't say much more about it, but what this says is the following, that the plume mass varies diurnally by a factor of 8 because of the opening and closing of the fractures on a daily basis, but the maximum mass varies over 13 years by a factor of 2. The plume exhibits all 3 periodicities, but with a phase lag. And this tells us that orbit variations are what modulate the variations in the eruptions. And this gives us the power of prediction. This lets us know that however long we want to go back to Enceladus, if we want to be there in 2040, we can tell you how bright the plume will be, how much mass will be in it. And so we don't have to, we can even use that information, of course, to properly design instruments. So I thought that was a pretty cool result. Vertical mass profile, how am I doing for time? Okay, vertical mass profile and sample collection. So this is another thing that I did recently with my group. We just grabbed brightness, scanned across the image, but now in very narrow vertical slices or slabs, plotted this up, altitude versus the average brightness, and if with assumptions of measurements, with assumptions or measurements from other instruments of particle size distribution, and assuming a light scattering law, these are small particles, so we assume diffraction scattering, me scattering. Brightness can be converted to mass at each altitude, so we can tell you what the mass is at each altitude. And that means we can say what one transect through the plume, a spacecraft flying through the plume, how much material it'll pick up. And so we've been able to do that, and 50 kilometers is the number we often give because that's the lowest altitude that Cassini ever flew. Yields a column density from 0.5 to 9 microliters per meter squared, depending, of course, on the time and the day of the year, time of day and the year that you arrived there. And so what, I guess I'm not ready to do this, am I? Okay, so anyway, we've been able to say how much material is in the plume. And from our imaging data, it seems like it agrees well with the other instruments. So we think we have this understood pretty well. So here are just some thoughts about where we are and what we should be doing. Confidence level to me is the holy grail in this business of going in search for life. Figuring out what biosignatures we want to look at and what confidence level we attach to them is extremely important, because if we're going to invest a lot of energy into going after searching for life, we want to come back with a really good and high confidence level. And a lot of the biosignatures that I hear discussed don't strike me as being ones that we'd really be able to say with 100% that we found life. So I scratch my head. What would it take? Well, I think it would take an image or a video of organisms. That's not surprising coming from an imaging person, but it's really true. Seeing is believing. So I really would like to see anything we do in the solar system. Exoplanet people can't do this, but in the solar system, we can actually put our hands on material that came from an ocean and take a picture of what's there. And so I'm hoping that any mission back to Enceladus for sure, and any other place that offers this type of accessibility, carries a microscope. You need slow capture so that you don't destroy the organisms you want to see, but that requires less than 2 kilometers per second fly-through speed. So let's go after, along with biochemistry, images won't tell you anything about biochemistry, but let's be sure to include microscopy. What would we expect on Enceladus by way of the number of cells? Well, if it turns out 10 gigawatts is about what we expect is coming out of Enceladus. I didn't even mention the fantastic work we've done together, combining our images of satellites with ground-based images of Saturnian moons that go back to the late 1800s, giving us a really long time baseline. We've been able to measure the secular increase in the orbit of Enceladus and the other satellites as well. This has allowed us to actually measure the Q of Saturn. And so that's a whole story. It's a very exciting story. But out of this new result, we say that 10 gigawatts is about what can be injected into the body of Enceladus. If 10 gigawatts emerges from the seafloor under the south polar terrain, you can measure what the heat flux is. It turns out it's identical to the average flux coming out of the mid-Atlantic. So that's very nice. It says the cell concentration at hydrothermal zones at the bottom of the Enceladus ocean could be the same as that on Earth, at least in those regions that are anaerobic. And that's about 10 to the 5 per milliliter. There's a process that happens in every natural body on the Earth called bubble scrubbing. It's whereby organic materials and organisms which are very hydrophobic attach to bubbles as they rise through the water column. And this has the potential for increasing, it scrubs the column of organic material, but at the surface, the bubbles break, they release their spray, and that's what we think we're seeing on Enceladus. So it can increase the organic load because organic materials that aren't part of cells do this, and the number of cells up to 1,000-fold. So that helps us a great deal. Even though it looks like there's very few cells there for actually grabbing and imaging or measuring, that helps a lot. A lander is the best possible mission. Why? Because an Enceladus material is going up and it's falling down. All you got to do is land on the surface. And I was fond of saying, look up and stick your tongue out, and you've got what you came for. Okay, so you can continuously collect material as it slowly falls. Over the course of 100 Enceladus days, you could collect, I think, a substantial number of cells on a target that's 8 inches by 8 inches. And if you don't have a lander, multiple slow fly-throughs of the plume would do also. So I wanted to say some other things. I think I have, do I have? I'm okay? I just wanted to say that I think we'd probably all agree the most interesting find we could ever make is to find life that was not like earthly life. The trouble there, you all know, is we're not really sure what to go in search of. In the Saturn system, Titan probably is the best body to do that because it's a Titan fan over there who's cheering. It's just covered with organic materials, methane, ethane, and so on. There's no oxygen in sight. And I mean, if there's any place to do it, it would be there. The problem with Titan is kinetics. It's 300 and something degrees below 0 Fahrenheit. And so it's not clear that even if processes would bring about life if it has happened on Titan. So Enceladus is, again, to me, and to those of us who think like this, is the best possible choice for going and knowing what we're doing when we get there. And then the next most interesting thing to me is finding a second instance of the origin of life. And to do that well, to really be confident you have it, is to go to the outer solar system, because the chances of interplanetary exchange at Enceladus, before anyone considers the effect of atmospheres in how material gets out of the Earth and into space in an impact, the chances of contamination from Earth at Enceladus is less than 2 times 10 to the minus 9. But at nearby planets like Venus and Mars, the probability is 10%. So I think we should be going after the target that would tell us, even if we found biochemistry like ours, that it was not life that had originated on Earth. And so, anyway, I hope I've convinced you. Enceladus is the place to go. Thank you. We've got 5 minutes.
Plenty of time for questions.
Okay, yeah. So, questions? Morgan.
Hi, Morgan Cable, JPL. Fantastic talk, Carolyn.
Thank you.
I wholeheartedly agree that Enceladus should be top on our list of places to explore.
Okay.
And one thing that you mentioned in looking for cells, that yes, that is something that would be considered a biomarker, but Carl Sagan once said that life has to be the hypothesis of last resort, right? So I want to strike home the point that we should be looking for multiple independent lines of evidence, and cells can be one of them, but other biomarkers as well, for example, amino acids, and you've heard this whole story before, but just emphasizing that we need more than one sort of smoking gun saying, yes, it looks like there's life there, to convince us and to convince, the community as a whole.
I certainly did not mean that we only go looking for an organism. I think I said that. Biochemically, it wouldn't be interesting at all, but it would be, you're not arguing that we don't have life here, because look, that's what I'm after.
What's the terrain like in small? In other words, would it be suitable for a rover?
Would it be suitable? Well, just so happen to have. This is a picture of the region on Enceladus that is the most jet active. Okay, it's the hottest region measured by the thermal infrared instrument, because that's where most of the latent heat is being deposited. And you're not roving on a place like Enceladus. This is 24 meters per pixel, but if I showed you pictures we took where we got like 3 or 4 meters per pixel, it's rocky, big blocks of ice and so on. You're not going to rove. I don't know what we'll do. We'll hop. I don't know. But there's no atmosphere, you can't use a drone. So this is on Damascus. Here's another region near the South Pole on Baghdad. And let me just say this, let me just finish that thought. You don't need to rove, because there's material over this whole region, there's material going up and falling down on the surface. It's just, if you could get to the picture I showed you before, then you'd collect the most material. But if you could land, I should say another thing. Enceladus's magnetic environment is benign. I mean, compared to a place like Europa, it's benign. You wouldn't have to worry about having your spacecraft fried or organic material being destroyed by the magnetic environment. So you could stay there for a very long time collecting material. Yes?
Speaking of Europa, though, what about the lifetime of the heating on Enceladus? It seems like there's some debate over that.
Speaking of Europa...
Well, so Europa, for instance, people think that the ocean's been there for billions of years, whereas it seems like there's much more uncertainty over the lifetime of heating, the longevity of the heating for Enceladus, which could be a problem for life.
I don't think that is true any longer. It was true when we thought that the maximum amount of heat that you could get into Enceladus was about 1 gigawatt. And of course, we were measuring 5 gigawatts, so that was like, we didn't understand that. But now it looks like 10 gigawatts is easy. And it's not impossible that it lasts, that the ocean is actually continuously active, even if it goes through a cycle where the heating is less. Yes?
How universal? Can you?
Yeah.
How universal is the physics that you described for Enceladus in terms of the geysers? Do you expect similar plumes in any icy object, including Europa or others? Can you elaborate?
Well, it's really simple. The mechanism by which the stuff gets out starts with an ice shell that puts pressure on the ocean. So through hydrostatic pressure alone, the water will get through any fractures that are there, up to a level of 92% the thickness of the ice shell if the ice and the water are pure. You put salt in it, and it changes the densities a little bit, but it gets very close to the top. just from hydrostatic pressure. And then the rest of the way, it makes it out the rest of the way with the exsolution of volatiles, and there are volatiles there, and also boiling. I mean, it doesn't boil because of temperature, it boils because of the release of pressure. So it will make it out the top. But there's other things you have to consider. On Europa, someone's recently pointed it out to me, it's a bigger body. So at the base of the ice shell, it's not clear that you can actually get cracks to open and stay open. On Enceladus, you don't have that problem. So maybe its small size actually has advantaged it. Yes, hi.
Hi, Caroline. Good talk again, as usual.
Thank you.
Could you tell us a bit more about the radiation environment of Enceladus? And you mentioned a lander that could survive for 100 days on the surface. Do we have the technology to do this, considering that Enceladus is very close to Saturn, so the magnetosphere is important?
Okay, so I didn't plant these questions, I mean it. But that was the other thing I would have said if I had enough time, because I came prepared with this. This is in one of my papers. I can only compare it to Europa, because that's all I know. I mean, that's the comparison I can make. But the flux per MeV at Europa, and I'm going to give it to you in 0.1, 1, 10, and 100 MeV intervals, the flux of Europa, the ratio of the flux on the surface at Europa to Enceladus, and I think this is an electron flux, is 500, 20, 10 to the 5, and 10 to the 9. So vastly more radiation flux at Europa than Enceladus. As far as just how in absolute terms the radiation environment at Enceladus is, I can just say that we've been there with Cassini. Now, we didn't hang out in that we're on these long elliptical orbits, but there's nothing ever suffered any degradation due to the magnetic field. Magnetospheric environment. And then bear in mind that Saturn has that glorious set of rings, and the rings absorb all the stuff in the inner magnetosphere. So that helps keeps it benign. Wait, did you have another question? That was it? Yes, I'm sorry.
You never mentioned about the temperature expected within the oceans and how this corresponds to our understanding of biochemical reaction on Earth.
I'm sorry, say that again. It's what do we expect the temperatures to be?
And how this match our understanding of biochemical reaction on Earth.
Okay, I mean, it's liquid water, so it's, at least 273 degrees Kelvin, and the hydrothermal regions, I told you this is the cosmic dust analyzer experiment, found silica particles. Well, they interpret what they found as silica particles. They're nanoparticles. They're very, very tiny and very monodispersed. They don't have a large particle size distribution. And that is like the sign of particles that were formed, that came out, or I guess, precipitated in a colloid. Okay, the idea being hot fluids coming out of the core and hitting the cold ocean. That and the alkaline nature, I don't know where they get the alkaline from, but anyway, that was their result, and they just made a complete analogy with Lost City. So Lost City is low temperature. We're not talking about 500-degree smokers. We're talking about 100 Celsius. Is that what you wanted to know? Yeah.
So how come Enceladus hasn't lost all of its oceans? Is it because some of the plume snows back down?
Well, the vapor comes out. There's more vapor than particles, but this.
Just, I mean, like over a very long time.
I know, and I get asked this question all the time.
I know, because I didn't hear it discussed in the talks. That's why I was asking.
I know. I get asked this question all the time, and I just always forget to do this calculation. But I think the answer is that we're billions of years away from losing Enceladus because of this. So I don't think we have to worry.
Is there a good simple model for the actual events? Like what's the cross-sectional area of one of these events?
Yes. Yes, there is. The strains produced by the stresses give you on the order of about 0.5 meter, okay, max. But there's also reasons having to do with trying to match the latent heat the thermal observations and the amount of mass flux, there's reasons for thinking that the vents actually are even maybe only 10 centimeters. So they're very thin. I mean, they're very narrow. Bill?
Your estimated range of material pickup on a pass-through of like 0.5 to 9 microliter, how many pass-throughs do you need at this sort of low velocity, 50-kilometer altitude, do you think, to have a high confidence of getting enough material to make definitive measurements of biology?
Well, there's one instrument I know produced this, the microfluidics instrument being developed at Berkeley. And these numbers don't give them any pause at all. But it would be very, very, very much better for lots of reasons to either have multiples, either go in orbit around Saturn and keep flying through the plume, or go in orbit around Enceladus and fly through the plume, or land, because that just increases your duty cycle. So, but you know, the real answer to this is we flew through the plume with Cassini and we did it. I mean, we've done it already, so it can be done again. Yes? Oh, sorry.
So given the geometries and energies that you've understood from the geysers, is it possible to get a map of the likely regions of higher surface deposition?
Okay. Yes, it is, and I think that's already been, I know it's been produced. I don't know if it was produced in what I would call the right way, but it is absolutely possible. Because we published in our paper, we give the location of every geyser and its orientation in space. We don't have mass production rates for every jet. That is such an enormous task, I don't even know if it's possible to do. But it is possible to get estimates. And I did this in a paper that I published with my research group in I'm losing track of time, 2017, in a special issue of astrobiology dedicated to Enceladus, where I estimated how much snowfall would fall on a collector plate, and that's how I got all these numbers for how many organisms you might collect if you could do that. Yes? Are you? No. Yeah, I think so.
You mentioned that Europa is one of the widest, Enceladus is one of the widest objects that you've seen. Have you measured the albedo for the satellite?
Oh, we knew that.
More importantly, has this albedo changed over time because of the deposits?
No, these things have been going on for probably millions of years. So no, it wouldn't change in our lifetime. And I don't know if they've detected any small changes, but its albedo is 1. It's the brightest, whitest object in the solar system, and we know now it's continuously resurfaced with frost, new frost. One more. Okay.
Hi. I'm curious if you can say anything about what the vents, or what happens to the vents after one of the large plume events. I'm curious, for instance, with an ambitious mission maybe, to have small flyers try to go down into the vent, and if you could say anything about knowledge through the vent.
Okay, you're asking me what are the conditions in the vent?
Correct, yes.
Okay.
And after a plume event, then does it crust over, or what,
well,
if there's any other information?
Okay, I thought of showing it, but I didn't have time. We planned sequences of images where everything was the same, the geometry was the same, and we were taking the same picture of the geyser field only maybe 2 weeks later, and we actually see jets going on and off. And they go on and off for reasons you just alluded to, that there's condensation of material, of vapor, in the upper part of the conduits, and after a while they just clog. And maybe they open up somewhere else, that seems to be. So individual jets stochastically go on and off. The time scale estimated for this is probably 18 months, 2 years, something like that. But overall, the plume never disappears. It just goes to a low level. There's always some jets, Even when you're in your maximum compression state, there's still enough open that material gets out. And that range I gave, a half to 9 microliters per meter squared, that half refers to the plume at its, obviously its faintest during the course of a day. Okay.